Welcome to this video produced as part of the Further Maths Support Programme's material for A-Level Maths and Further Maths. This one focuses on work, energy and power, and the first section of it is work and energy, and in particular in this case work. Well, what is work? A good question for any student. Work is done when a force is applied to an object and the object is moved through a distance. That's the physical idea of work. And it's a scalar quantity rather than a vector, and it's defined to make that concept precise. The work done by a constant force is force times the distance moved in the direction of the force, or a component of the force. That's the important thing. If the force and the direction of movement are different, it implicates components in order to do the calculation. Now, I've stressed throughout the importance of the standard units, meter, kilogram, second. When we go into work, that must mean, since it's a force and a distance, a Newton meter, and that has a name, the joule. But joule doesn't mean anything else other than a Newton meter, so you could perfectly well dispense with the name joule. It's not necessary, but it's just convenient. It saves using words. Now, if work is a scalar quantity, on the same time, a force or rather its component, could be positive or negative. So you can end up with a work expression which is positive or negative. It's possible to calculate work done by a variable force, and in fact that's the ultimate objective in dealing with any kind of mechanics. But in the simple cases that we start with the basic concepts, the forces will be taken as constant, and generally also, as we've seen, the accelerations too. If there's movement on the part of a force, then work's done. If there's no movement, there's no work done. If there is movement, then you expect to have some kind of work as a result. Notice here you've got a picture of a weightlifter who's actually stationary, and at that point, although he probably feels he's making a great deal of exertion, he's not actually doing any work because nothing's moving. Though I think if you look closely you might detect a slight shake carrying a weight like that. Let's take a simple case, a sledge pulled along smooth ice, so we don't need to worry about friction and other complications, by a constant horizontal force of 45 newtons. If the sledge moves 10 meters, how much work has the 45 newtons done? Well, the point of application of the 45 newtons moves 10 meters, so that's a simple question to answer. We simply use the definition and we say that it's the force, which is 45 newtons, times the distance, which is 10, which gives us therefore 450, and the units will be joules, or if you prefer, Newton meters. There we are, and I've put the units back in when I've answered the question. So that's a simple case. You couldn't really ask for anything more simpler than that. Now let's look at a situation where you've got a similar setup without friction, but you've got the rope inclined at an angle. So let's take the sledge pulled by a rope at 50 degrees, and the tension is still 45 newtons and the movement still 10 meters. How much work's done then? Well, this time we have to look in terms of components. By the usual rules, the 45 newtons will have a component of 45 cos 50 in the direction of movement. So that's the figure that we must use in doing the calculation. So if we want the work done, it will be 45 cos 50 times 10. Now there's the two diagrams side by side to show the forces. As a rule, it's not a good idea to show components on a diagram. If you do, you end up concluding that there are more forces than really there are. But just for this particular case, to show the comparison with the previous situation, the bottom diagram shows the components in the component in the direction of movement. So to do the calculation then, it's 45 cos 50 times 10, and that will need a calculator. but otherwise it's just numbers. So there we are, there's the calculation done, and it's 289 to 3 significant figures, so the answer to the question is that the work is done is 289 joules. Compare it with the previous answer, which was that it does 450 joules, you see, so it's considerably reduced because of that interference of the cosine. Right, we press on. So that brings us to the end of this particular video presentation. The next in the same series will be on the concept of kinetic energy. I hope to be with you later to explore that.